Okay, let us begin. Good evening. Welcome to our Saturday discussion and presentation. I think it's January 15th, 2022. This is the third in what is going to become a five-part class series around the question that honestly so many people want to have a sense, they're really looking for a sense of how to come up with the solutions to the crises that we face. And as we've seen with the previous classes and presentations, people want to arm themselves with the sense of what to do, how to solve the problems, how to overcome these challenges. And fundamentally, what we want to impart upon people is the capability and access to rediscovering the principles that really govern this universe, that govern this nation. And it's really important to emphasize that these are principles that we must rediscover and apply in a new fashion. So I think Bruce is going to be giving the key presentation here, and then we will start with the question and answer. I'm sure there's going to be a lot of provocative things that people will want to talk about and discuss. So I will hand it over with no time to waste to you, Bruce.
All right, so it's good to be with you. For those of you who watched the dialogue last week between me and Dan on the question of poetry, where Dan Leach educated us on the principle of poetry and metaphor. Tonight, we are going to extend that discussion, building up on what Dan had presented, to the application of metaphor to science. If you weren't able to see it or didn't watch it, the dialogue is posted on our website, and I strongly urge you to go back and read it or listen to it, because I think that'll give you some real insights into what I'm going to be discussing tonight. Now, this presentation tonight is actually based on two papers by LaRouche. One is a paper from 1979, which was published in Fusion magazine, called "Poetry Must Begin to Supersede Mathematics and Science." I can tell you that this was an extremely provocative title, and the subject matter of the article was equally provocative, both to myself and I'm sure the hundreds of thousands of people who read it at the time, because it set forth a new standard for scientific thinking that's appropriate to economics and politics, but then redefines the appropriate standard for science, going all the way back to the ancient Greek science and probably beyond, but those are the written records that we have. The second article is called "On the Subject of Metaphor," which LaRouche wrote while he was unjustly imprisoned at the result of a malicious prosecution that was headed up by none other than Bob Mueller, under the direction, at the instigation of Henry Kissinger and George H.W. Bush, which of course is a very significant point in history. All the things that people are seeing coming out now about the Russiagate, the attacks on Trump, the Mueller report, this was all these things, the way the January 6th prosecutions are being run, the politicization of the justice system was all pre-run initially against LaRouche, beginning in the early 1980s, shortly after this document, this first document was written. And then he wrote the second one on the subject of metaphor, which was published in Fidelio magazine while he was in prison. He discusses this subject in many other places, but I think these two are the best comprehensive places to get started. And it's totally appropriate that we reintroduce or reemphasize this idea of metaphor in science at this point in history, because it's essential for us to be able to build an educated citizenry on what the basic principles of economics are. And as LaRouche emphasized many times, it has nothing to do with statistics and mathematics. It has to do with the creative principles of the mind. And that means one has to understand how the creative principles of the mind work. Now, Dan gave us a lot of insight into that in the discussion of poetry, because that's what poetry is, as was demonstrated last week. Poetry is, in effect, the mind expressing how the mind creates, the creative process. We saw that in the poems Dan chose on Chapman's Homer, Ode on a Grecian Urn, and To Hope, 3 poems written by John Keats, who in our discussion last week, we felt it totally appropriate to adopt as an American poet, even though Keats spent his life in England, because of the crucial role that Keats and other great poets played in the creation of the United States and the building of an educated leadership and citizenry in our country. And these principles of poetry are essential today if we're going to be able to steer this country away from a disastrous direction that is being led into, and into one that is hopeful, optimistic, and progressive for the future, that is based on science and technological development. What we call re-Americanizing the US economy, which does not mean reshoring only. Yes, we have to reshore, but we have to get the economy back on American principles. And that's why it's appropriate to talk about re-Americanizing the economy, not simply reshoring or restructuring or anything like that. And for that, we have to understand what these American system principles are. Now, prior to LaRouche, these principles were elaborated by Hamilton and others and practitioners like Lincoln and the Carys and Roosevelt and so forth. But LaRouche gave a unique contribution to the understanding of the underlying scientific principles on which the American system of economics was based, and really laid the foundation for how that can be developed and accelerated for future economic development. So we have to understand these principles, and that means we got to understand the principles that LaRouche presented to us. Now, this is very crucial right now because everybody, whether they're Democrats, Republicans, liberal, conservative, are completely confused on this. Although some people have an instinctive idea that the key missing element in our economy is the development of the creative powers of the human mind and the development of technology and science and so forth, that we have to get back to that being the central core of our economy. Although we have to define technology properly, not in the way it's defined in Wall Street, which includes everything from video games to new forms of new forms of virtual reality. I guess they call it metaverse. But real technology, the technology which actually increases the productive powers of labor. So we have to redefine technology, but we have to, so people have an instinctive idea of what that means, that that's the direction we have to go. But they're really confused because they're caught in trying to understand economics based on mathematics and statistics. Take, for example, the current discussion about inflation, which is devastating the country right now, especially the lower 90% of the population who are not benefiting from the inflated asset bubble on Wall Street and all kinds of financial assets, but instead are seeing their wages and savings shrink. The value of their wages and savings shrink as the prices of the goods and services that most people spend most of their money on increases. But if you look at the whole discussion about what to do about inflation, most of it involves trying to manipulate statistical parameters, such as interest rates, et cetera, money supply, and this kind of thing. And they have great passionate debates about whether the Fed should shrink the balance sheet, increase the balance sheet, do this, do that. And it seems like everything the Fed does and everything the government does and all the regulations and all the manipulations of these kinds of statistical parameters always seem to have a deleterious effect on the actual productive capacity of the economy. We saw this in 2008, where manipulation, where the financial blowout led to a physical economic collapse, massive unemployment, shutdown of industries, and so on and so forth. And Bernanke and Geithner went to work basically manipulating statistical parameters, which had the net effect of bailing out the banks and screwing the American people. And then you had a similar thing under COVID, and the same thing happened. They supposedly this time were going to help the American people, but the American people have been screwed by the measures they've taken. But Wall Street and financial oligarchs have benefited, and the control over the financial system has actually become increasingly more concentrated, and they once again got the bailout. So we can argue, I mean, that's obviously unjust, but it's also wrong. But you're not going to fix it by arguing about what to do about interest rates, money supply, et cetera, et cetera. You're only going to fix it by changing the basic parameters under which you measure and the development of the economy, and take the kind of measures which will produce the physical economic results. Then you can calculate your results based on some statistics or mathematical measures, but you don't do the reverse. You start from the top. Now, that means we got to have a better understanding of what are the scientific methods that have to be applied to the economy. Now, to do that, let me start first with a couple of examples that will at least illustrate the point in more simplified terms. Let's take, first of all, two major discoveries in physical science, which exemplify what I'm talking about. One is Kepler's discovery of the elliptical orbits of the planets, the actual discovery of the principle of gravitation. Now, we've presented a lot of material on this, and it should be the central point of basic education in the United States. I mean, people are all worked up about critical race theory, and they should be, and it shouldn't be taught in this country. But what's just as criminal, or even more criminal, is what's not taught, which is basic principles of science. And children go through high school, all the way up through high school and generally through college, and get no acquaintance at all with Kepler's major discoveries, except if they're lucky, they may get a list of Kepler's 3 laws. Well, and one of his 3 laws is that the planets orbit around the sun in elliptical orbits, and the area that's swept out between the planet and the sun is equivalent to the time elapsed. Now, I'm not going to go through the details of that. As I said, there's a lot of articles that we put out that describe that. But the fundamental principle here is that Kepler completely revolutionized science by attacking and addressing a false conception about the way the universe works. Prior to Kepler, it was generally believed and accepted as an axiom, as a dogma, that everything in the physical universe had to proceed and move according to straight lines or perfect circles. And of course, a straight line is nothing more than an infinite circle. And the reason why was because the circle is the geometric figure, which is uniform. The angle that the circumference makes to a line connecting the circumference to the center is always at 90 degrees. You could think of this very simply, that if you put a blindfold on and you tie a rope to a stick, and as long as you walk blindfolded, a stick in the ground, and as long as you walk blindfolded, keeping that rope taut and walking at a 90-degree angle to that rope, you will walk in a perfect circle. You don't have to think at all. And this idea that because this was the simplest and most perfect of all figures, that the planets moved around the sun in perfect circles, and that this had to be the basis for all physical action in the universe. However, when you looked at the motion of the planets and studied that and how they actually move, that was not the case. It had been known for millennia that the planets speed up and slow down during the course of their effort, their orbit. They get brighter and dimmer. And then, of course, at sometimes they actually appear to go move backwards and make little loops. So there were lots of various schemes, mathematical schemes that were devised by Ptolemy, by Copernicus, by Tycho Brahe, by others that tried to account for this observed irregular motion as the compound of various circular actions by adding epicycles and so forth to the circular motion. And Kepler studied this very carefully, and he had the benefit of some very precise observations made by his one of his collaborators, Tycho Brahe, the Danish astronomer. And he studied the orbit of Mars very, very carefully. And he found that the best possible approximation of the Mars orbit using circles was always 8 minutes of an arc off. There's a tiny discrepancy. Now, he could have discounted this discrepancy as simply an error in measurement. But he didn't, because he realized that there was a problem in the fundamental dogma, the fundamental axiom of the science. And that was that the universe obeyed perfect circles. And Kepler was a student of Cusa, and Nicholas of Cusa, or not a student, but a follower of his writings. He lived much later. But Cusa argued that the universe, the physical universe, could never operate according to perfect circles. That the physical universe had a character of non-uniformity to it. And this enabled the physical universe to have a characteristic of perfectibility. In theological terms, the idea was, is the universe perfect? Is that the most perfect thing? Because if it's perfect, it can't become better, which means there's something it can't do, so it's not perfect. That's a little philosophical paradox there. But Cusa said, no, it's not perfect, to be perfect, it has to be able to perfect itself. It has to be self-perfectibility. And that meant that the physical universe had the capacity for non-uniform motion. Now, that, again, just look back at this example of the trying to walk in a non-uniform, in a circular path, blindfolded. You don't have to think, but to make your motion non-uniform but regular, you have to have some principle you're governing. When do you speed up? When do you slow down? When do you get closer to the stick? When do you get farther from the stick? This you can't do without some thought, so to speak. Well, Kepler said that the physical universe has in it a kind of thinking, which is not conscious human thinking, but it's what he called a species, which is the Latin equivalent for the Greek word idea. And that idea is gravity. He didn't say gravity was an attractive force. He said it was a principle that governed motion. And if the planets were moving in a pathway that brought them closer and farther to from the sun during their orbit around it, the motion of the planet would speed up and slow down. And thus, the best figure for that would be an ellipse. And so he approximated the planetary orbits by saying they moved in ellipses, not circles. Well, that's a complete revolution in science, because it overthrew a mathematical dogma which was imposed on the physical universe, a false axiom assumption, and replaced it with an actual physical principle which was based in the actual experimental evidence, which was the observations of the planetary motion. And the universe, the planets moved in elliptical orbits long before Kepler's discovery didn't create the elliptical orbits, but Kepler's discovery changed everything about science, because a universe that has principles which are capable of change, non-uniformity, is a universe that's completely different than one that's chained into uniform motion. And this created a whole revolution in science, which we can, which should be taught in school. This should be like 7th and 8th grade physics and math should be the working through of all Kepler's works. Could replace all the formal stuff and just teach students this, and they would learn everything they need to know about trigonometry, geometry, algebra, etc., even calculus. In 7th and 8th grade, and they'd be a lot more excited about it. So the universe was completely different. It was a change, it was a revolution in scientific thinking, and there's no continuous process that takes you from perfect circles to ellipses. It's a leap. It's a change, a complete change in thinking, which reorders everything you thought about everything else. And if you think about what Dan presented to us last week about poetry, you can see that's exactly what poetry does. You start with a certain ideas, and as you go through the poem, your mind is the poet leads you through a series of transformations in your thinking, which are discontinuous, one from the other, and create a new concept that you previously didn't have, and you become a changed person. And of course, a great classical poet, like a great classical piece of music or any great classical art, is so well composed that you can keep going back to it and going through that process, and each time you have the same experience, not the same exact experience, but the same experience of a discontinuous leap, of a further deepening of your understanding, of a change in your thinking. I think that's a really easily accessible example. Another one I would just point to without elaborating is Einstein's discovery of the general relativity and also special relativity. and his and Planck's discovery of the quantum of action. This ushered in a complete revolution in science because one had to change the way you were thinking about the universe as a whole. Prior to this discovery, there seemed to be the universe seemed to be divided into two types of processes: discrete processes like physical objects and particles, and continuous processes like waves, electromagnetic waves or light waves, etc. And there was plenty of experimental evidence to indicate that these two different and discrete and different and fundamentally different processes existed. What Einstein and Planck showed was that this distinction was a mistake. It was not correct. It was an assumption that light can behave like a particle and particles can behave like a wave. And they proved this. They proved this both theoretically, and people following their theoretical discoveries proved it experimentally. And the same thing with general relativity, and special relativity, which completely got rid of the idea of absolute space and time, which of course Leibniz and others previously had understood. But this was a real transformation. So this has still not been resolved. And in fact, what happened in the beginning of the 20th century is that this discovery was basically brushed over by simply creating a mathematical construct that used statistics to try and understand or model this behavior of physical processes. But it didn't, and that enabled the application. You have to admit, it enabled the application of this experimental evidence for things like, solid state physics and all kinds of things which have been developed into advanced technologies. But the understanding of what that meant for the nature of the universe itself was never explored because no one wanted to deal with the underlying assumptions which they had to deal with. And Einstein, even though he was the great discoverer of this principles, was ridiculed for stubbornly insisting that science had to address this axiomatic question. And he was basically disregarded for the latter 2/3 of his life. But those are two examples. Now, when we're dealing with economics, you're dealing with something that involves a more complex situation. You're dealing with the interaction of physical processes like what I talked about with Kepler and Einstein. You're dealing with the relationship between physical processes and living processes, living organisms, and you're dealing with the role of the human mind in organizing living processes and non-living processes in such a way that the creative powers of the mind and are increased, and the productive powers of labor is increased. And an economy organized for the purpose of increasing the productive powers of labor and increasing the creative powers of the mind is an economy that functions. And so however you organize these other parameters that I discussed that people talk about as economics is incidental, it's ancillary to the scientific principle of understanding the economy as this interaction between human creativity, life, and non-life. Now, the key element here is that in some situations, like in a closed physical system, like a heat-powered machine, there appears to be a tendency of the physical system to appear entropic. That means it tends towards equilibrium. It tends to go from a state of high potential to a state of low potential. But living processes exhibit an opposite process, a process which goes from lower states of organization to higher states of organization. And of course, the human economy does the same thing. In fact, as Dan showed us last week, the human mind does too, because you're a completely different thinker after experiencing an interaction with a great poet than you are beforehand. Just as you would be, just as Kepler enabled us to be, or Einstein. So you have this, what LaRouche called at the time, negentropy, which he never really liked that term. He often sometimes referred to it as negative entropy, but he didn't like that term either. And instead, he talked about a different process, which had the characteristic of organizing itself from lower states of potential to higher states of potential. Now, we see this expressed in a healthy physical economy, where the potential for increasing the productive powers of labor itself increases. So you go from lower potential to higher potential. You can measure this, as he often taught us, in potential relative population density. That is, the potential to support an ever-increasing population on a given area of land relative to the physical characteristics of that land, which you can improve. Desert land, you can make, take arid land and make it more habitable by irrigation and other forms of bringing water to it, and so on and so forth. So the physical economy, just like the human mind, is characterized by an anti-entropic process. Now, I like to use the term dunotropy for that, which in effect means dynamic change, a change from lower potential to higher potential. And the mind, the economy, the living processes, and the physical universe itself all exhibit overall a dunotropic tendency, an anti-entropic tendency. Now, LaRouche discovered this very early on. This was really the basis, the fundamental beginning of his economic ideas. And you can look at the class series that Brian Lance did back in December, where he presented an account of the early discoveries of LaRouche. And LaRouche was looking at that time, okay, how do I represent this concept of anti-entropic change, anti-entropy, in a scientific way? Now, in his efforts to do this, he became acquainted with the work of Bernard Riemann, who lived in the early to middle 1800s, and another German mathematician named Georg Cantor, who developed the concept of the transfinite. Now, I want to present to you a couple of aspects of Cantor and Riemann as a way of illustrating a metaphor in science that expresses an anti-entropic process. I'll start with Cantor. Cantor was a very interesting person because he came from a musical family. His great uncle was the leading violinist in Vienna who first performed Beethoven's late quartets. And Cantor himself was a trained violinist and played in a string quartet his entire life. But he spent his career as a mathematics professor in Germany. And he discovered something which demonstrates that mathematics cannot be relied on, but only the human mind can be relied on. So I'm gonna give you a little illustration of his discovery of what became known, what he called the transfinite. So I'm going to share my screen here. This is just a couple of illustrations, and I'm doing this very quickly. I'm not presenting the whole proof, but I just want to give you a little taste of it. So Cantor began with the simplest form of mathematics, or that what people would think would be the simplest form of mathematics, and that is, say, the counting numbers. I've written them down here. 1, 2, 3, 4, 5, 6, 7, and you could keep going forever, right? Very simple, involves only one idea, which is adding 1 to the previous term. So no matter where if you were wandering around and you bumped into a counting number, you could always find the next one, even if you hadn't started at the beginning. And of course, it's very easy to conceive of that this is an infinite series, that this goes on forever. Now, Cantor asked the question, are all infinite series the same? So let me pose a couple of examples to illustrate this. First, I'll ask you, well, are there just as many counting numbers as there are even numbers? Well, if you take the numbers between 1 and 10, there are 10 counting numbers, but there's only 5 even numbers. So you would think, well, how can there be just as many counting numbers as there are even numbers? Well, if you actually compare them this way, you can see that you take the counting numbers and you put the even numbers underneath them, and the counting numbers match up 1-to-1 with all the even numbers. So Cantor said, well, these two counting numbers and the even numbers have the same cardinality. They have the same, or another term he used was power. They have the same power, transfinite power. They're both infinite, but they have the same transfinite power. Now, he asked, well, are there other transfinite powers? So he said, well, how about all the fractions? Well, this would seem like it would have a higher power than the counting numbers, because the fractions just between 0 and 1, there's an infinite number of fractions, a half, a fourth, third, 3/4, et cetera, et cetera. So you would think that would have a higher power. But if I can list the fractions in this way, in this chart, 1/1, 2/1, 3/1, 4/1, 1/2, 2/2, like this, I know that if I were able to keep doing this process indefinitely, I would not miss a single fraction. And consequently, if I then arrange them this way by drawing a diagonal, I can create a string that basically lists all the fractions in such a way that they match up 1-to-1 with all the counting numbers. And when Cantor discovered this, he said, I see it, but I don't believe it. How can that be? He continued his exploration for looking for an infinite set, an infinite aggregate, he called them, that had a higher transfinite power than these, what he called denumerable aggregates, that is, aggregates that can be lined up 1-to-1 by some ordering principle in which you are definitively define achieve every element of the aggregate is equally defined. So he looked at other numbers that were not fractions, or said, well, let's expand our concept of numbers. So he thought about these kinds of numbers, which are represented by the ratio of the side of a square to the diagonal, which some people call the square root of 2. It shouldn't be called that. It's really that the diagonal is the line that has the power to make a square whose area is 2. That's the way the Greeks thought of it. So these are powers. And but these two, you cannot, these two, this line, the diagonal of the square and the side of the square are incommensurable. They cannot be expressed by any rational process. It's only by an infinite process. And I'm not going to go through the proof of this because it gets a little bit complicated, but Cantor proved once again that all such numbers, like the line which has the power to make a cube of 2, or whatever, there's an infinite number of them, and they too, they're called algebraic numbers because they were called algebraic numbers because they're solutions to algebraic equations. And these numbers too have the same power as the counting numbers. They don't get you anything new. Then there's another type of number, which was discovered by the Greeks, but really not known. Its uniqueness was not known until Cusa, which was this one, which is the ratio between the relationship between the diameter of a circle and the circumference of the circle. Now, this is a completely different type of relationship because, as Cusa said, it's the relationship of the curved to the straight. And the short answer, the short symbol that the Greeks gave, the name the Greeks gave to this number is pi. So Cantor said, well, what if I add these to the algebraic and counting numbers and fractions? I look at the transcendental numbers as well. And he showed by this method, another diagonal method, that if I represent these infinite numbers in this way, I can always make another number by taking the diagonal and making a number that the first term of my new number is different than the first term of the first number. The second term is different than the second term of the second number. The third term is different than the third term of the third number, and so on and so on and so forth, that this number I create will always be different than anything I've been able to list. And this indicates, he said, this proves that this number, the number of all transcendental numbers, has a higher transfinite power, a higher cardinality than all the other, than the denumerable transfinites. And so he called, well, in different writings, he gave these different names. So I'm not going to go into it because it gets very technical and very, it's like a very complicated puzzle, but it's a very fun puzzle to explore. But nevertheless, here you have an example of something in mathematics, which appears to be very precise and logical and deductive, which actually can only be understood as a type of metaphor in which there's a discontinuous leap between the cardinality, the power of denumerable transfinites, the lowest transfinite, and the power of what Cantor called the continuum. Now that may be a little abstract for people. Some of you may get it, but I introduce it because it is a central point that LaRouche relied on to develop his concept of a physical manifold in which you have a state of an anti-entropic process, a negentropic process, an economic process, or a physical process which proceeds from lower to higher states in a discontinuous way. Now, I'm going to illustrate something from Riemann, which may be a little bit easier to understand if you had trouble with this one because it's visual. And a lot of times people have an easier time with geometry than they do with this expression. But this expression is very central to LaRouche's thinking. So I wanted to introduce it to you at least for you to get some more exploration on your own. So, and for this, we go back to Kepler. So, and Kepler built this up off of the ancient Greek idea of the 5 regular solids. And you can see in this picture, this is a drawing from Kepler's book, Harmonies of the World. And you can see that here we have the cube, the octahedron, the tetrahedron, the dodecahedron, and the icosahedron. And here they are sort of broken up. This is Kepler's own drawing. And this was a discovery by the ancient Greeks that if you take a sphere and you divide the sphere into equal parts, there are only 5 regular solids that can result. And this is a very fascinating proof and a very good one. Another one which should be introduced to children probably in maybe 6th grade or 5th grade. And they would have the experience of discovering a very, very profound principle of science just by learning that there are only 5 regular solids and can't be any less or any more based on the sphere. Now, you can divide the sphere up in other ways than regular. And here's some Kepler examples of irregular solids. And these are called Archimedean solids. And you can see that they're made up of different figures, like here we have the pentagon, a square, a triangle, square, and so forth. So these are all the Archimedean solids, and there's a finite number of those. And there are other types of spherical solids that are made. I'm not going to go into them, but this is another area that I think could comprise maybe a year of primary school geometry education, which would just kids would love, and it would teach them so much about how to use their minds to discover the physical world. It would stick with them for the rest of their lives. Now, there's another characteristic of this, which is it was discovered by, at least attributed to Leonhard Euler, who had a lot of problems and made a lot of stupid mistakes over his career. He was sort of in the early part of the 1700s. But he discovered a principle that any of these spherical solids, like the 5 regular solids or the Archimedean solids or any of these irregular solids, and this is another thing that you should experiment with, but you could also have kids do this. I actually taught a class to a few children back in the 1980s who are now quite successful doctors, businessmen, scientists, and so forth. And we had a ball doing this. But if you count the vertices of any one of these solids, you count the edges, and you count the faces, and you subtract the edges, the number of edges from the number of vertices, and then you add the number of faces, on any one of these solids, it will always equal 2. Now that seems like a strange curiosity. Why is it that no matter how you divide up the sphere, the vertices minus the faces plus the edges will always equal 2? Well, that's an interesting idea. But then Gauss and Riemann were studying, for other reasons, a different characteristic of geometry, which later became known as topology. Topology is the idea of the position, things that are beyond measure relationships, just fundamental characteristics. And they discovered that if you have a surface like this, which is a torus, that is distinguished from a sphere because of the hole in the middle. And so in this torus, you see there's a circle you can draw this way and a circle that you can draw this way. And neither one of those will cut the surface in two. So this surface has a particular characteristic, which Riemann called a genus. That's just the name he gave. There's all kinds of reasons for it. But they discovered that if you take this surface and you make solids on that, here's a crude drawing I made of a polyhedra made out of a sphere. I mean, out of a torus. And so there's a hole in the middle. And if you count the edges, faces, and vertices minus the edges and the faces on this one, there are 16 vertices, there are 32 edges, and there are 16 faces, and that equals 0. And no matter what kind of solid you make that has one hole in it, it will always equal, the vertices minus the faces plus the edges will always equal 0. And then if you extend it to surfaces like this, which have two holes, the vertices minus the edges plus the faces will always equal -2. And if you put a third hole, it'd be -4, etc. And this gets even more complex and really fascinating. But I present this to you just to illustrate the sequence, that there's a discontinuity between a sphere and a torus, between a torus and a two-hole torus. There's no in between. You have a sphere, and when you transform it into a torus, there's no place where it's half one, half the other, or part one, part the other. It's a discontinuous, it's a discrete thing. And yet, as they increase the connectivity is the term Riemann used, the way they're connected, the whole characteristics of what is of the capability of each surface changes. The quality of the solids, for example, that can be constructed changes discontinuously. So if you put these two kind of ideas together, the idea of contour and the idea of Riemann, you see that you have a kind of mathematical expression which actually serves as a metaphor for the actual nature of an anti-entropic process, of a dunotropic process. Now, where there's a discontinuous transformation from one concept to another that completely transforms the nature of the economic relations. Now, in the actual history of the economy, we can see several examples of this, like the introduction of the heat-powered machine, which completely transformed all physical economic activity, or the introduction of electrification, for example, or the development of the internal combustion engine, which transformed transportation, and the combination of these things. So we have examples in the development of the physical economy where unique physical discoveries, scientific discoveries, applied technologically, had transformative effects in a discontinuous way in the entire economic relationship. So this is the kind of mathematics which LaRouche emphasized is necessary for economic to model the economy. That any use of statistics or mathematical expressions are insufficient to develop this kind of economic understanding of the economy without except for this kind of examples, which I showed you with Gauss and Riemann. Now, if you think about this, this is very similar to what we experienced last week in the discussion of poetry, and what we will discover next week in the discussion about music. That in a musical composition, this is exactly the same process that the mind is educated on. So I will just end with this, that if we were to transform our educational system so that children were introduced to these ideas and this way of thinking as the fundamental part of the fundamental nature of their education, we wouldn't have any problem with bureaucrats who don't know what they're talking about. So why don't I stop there and open it up for questions?